2.3 Linear combinations and span. Linear combination, the definition is, let capital V be a vector space over a field capital F. Let small v1, v2, etc. vn belongs to capital V, and alpha 1, alpha 2, etc. alpha n belongs to capital F. Then the element of the form alpha 1 v1 plus alpha 2 v2 plus etc. plus alpha n vn is called a linear combination of the vectors v1, v2, etc. vn. So remember this shape. This can be written as sigma alpha I vi. That is, every term is a scalar multiplication of a scalar and a vector, no? The product of a scalar and a vector. So sum of all such scalar multiplications is called the linear combination of vectors. So whatever the vectors considered in that combination. So normally we write 2x plus 3y plus 5z. So this is called the linear combinations of the variables x, y, z. Here we consider the vectors v1, v2, etc. are vectors. So this is called linear combination of the vectors, right? Now linear span we denote by L of S. Let capital S be a non-empty subset of a vector space capital V. Remember, S is the subset of V and it is non-empty. Then the set of all linear combinations of the finite elements of S is called the linear span of S and is denoted by L of S. So what is S? S is the non-empty subset of V. And L of S is the set of all linear combinations. We know the linear combinations will be of this form, no? So if we collect all the linear combinations with respect to the finite elements of S, that collection is called linear span L of S. So this linear span will contain each element in the linear combination form. Okay. So the vectors considered in that linear combination will be the finite elements of this subset of V. Yes. That is, any element of L of S is of the form alpha 1 v1 plus alpha 2 v2 plus etc. alpha n vn. That is, every element of the linear span will be a linear combination form. Okay. So normally we collect all the scalars from the field F and vectors from the vector space V, and in the linear span the vectors considered belongs to the subset S of V. Okay, so let us next see linearly independent. Let capital V be a vector space over a field capital F. A finite set of vectors v1, v2, etc. vn are said to be linearly independent if alpha 1 v1 plus alpha 2 v2 plus etc. plus alpha n vn equal to 0 implies alpha 1 equal to alpha 2 equal to alpha 3 equal to etc. equal to alpha n equal to 0. That is, we say the finite vectors v1, v2, etc. vn are linearly independent if their linear combination is 0. When their linear combination is 0, all the alpha i's go 0. When we assume the linear combination of those vectors as 0, then if we find all the alpha i's are 0, then we say these vectors are linearly independent. The other cases v1, v2, etc. vn are linearly dependent if they are not independent. So not independent means again we consider the same combination to be 0. That is, the linear combination is 0. Then if not all alpha i's are 0, then we say the vectors are linearly dependent. That is, at least one alpha I we should find not equal to 0. So remember this condition. Okay. So for checking linearly independent or linearly dependent, our assumption is same. We consider the linear combination of the vectors which is to be verified, whether linearly dependent or independent. Though with respect to that, we consider the linear combination to be 0, and we need to get the values of alpha I if we find all the alpha is 0, then the vectors are linearly independent. If at least one alpha exists not equal to 0, then the vectors are linearly dependent. Okay. Now the problem show that V3 of R, the vectors 1, 2, 1, 2, 1, 0 and 1, 1, 2 are linearly independent. You know, V3 of R means it is a three-dimensional vector space. That is, every element will be in this form. Okay. So each entries in this point will be real numbers. So this is the shape. Now we need to prove these three vectors are linearly independent. Recall the definition for linearly independent. There we assume that the linear combination to be 0 and we need to find alpha I values. If all the alpha i's goes 0, then we say the vectors are linearly independent. Here we consider the first the 3 points as v1, v2, v3. So v1 is 1, 2, 1, v2 is 2, 1, 0 and v3 is 1, 1, 2. Now we need to prove this vectors v1, v2, v3 are linearly independent. So let us assume that the linear combination with respect to v1, v2, v3 as 0. That is alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 equal to 0. Now substitute the values of v1, v2, v3. So alpha 1 into or v1 is this one. That is the first point given 1, 2, 1. Plus alpha 2 into the second point 2, 1, 0 plus alpha 3 into the third point 1, 1, 2 equal to, we write the right hand side also in the same point form 0, 0, 0. So you know how to simplify this equation. So the collection of all the first elements will give you 0, the right hand side equate with the first element of the right hand side. So we get 1 into alpha 1, that is alpha 1 plus 2 into alpha 2, 2 alpha 2 plus here also 1 into alpha 3 plus alpha 3 equal to 0. So with respect to the first values, we bring the first equation. Similarly, consider the second values. So if you see the second values, 2 into alpha 1 plus 1 into alpha 2 plus 1 into alpha 3 equal to second element 0. Okay, so this is second equation. Now third, 1 into alpha 1. So this is plus 2. Here there is no alpha 2, the coefficient, the third value is 0. So the coefficient of alpha 2 goes 0. So we don't write the alpha 2 term. So that is 0 into alpha 2. We don't write that alpha 2 term. We move to the next term 2 into alpha 3. So see here 1 into alpha 1 plus 0 into alpha 2. We skip that plus 2 into alpha 3. This gives you the third equation. Alpha 1 plus 2 alpha 3 equal to 0. Okay, now we need to solve these equations. Solve equation 1, 2 and 3. So you can solve by any method, whichever you have learned earlier, by elimination method or determinant method, any method you can use. Here I consider the three equations here and I use the rule of cross multiplication. So if you find the first two equations, the coefficients are different. So I find two different rows, that is equations, no? So considering the RCM for 1 and 2 equation, I write the coefficients of B, that is alpha 2, 2, 1. So this is alpha 2 coefficients, 2, 1. And this one is 1, 1 here, okay? And 1, 2, alpha 1 coefficient and 2, 1. The code, you keep the code BCAB like this, okay? And these two, this in between this one, here the variables are alpha 1, alpha 2, alpha 3. So alpha 1 by this minor, okay? So alpha 1 by 2, 1, 1, 1. Alpha 2 equal to alpha 2 by this minor, okay? 1, 1, 1, 2, this one. Equal to alpha 3 by the next minor, that is 1, 2, 2, 1, like this. Okay. Now simplify alpha 1 by 2 minus 1. We multiply these two minus multiply these two. So 2 minus 1. That is 2 minus 1 here. Similarly, alpha 2 by 2 minus 1. Similarly, alpha 3 by 1 minus 4. Now simplify. Alpha 1 by 1. Alpha 2 by 2 minus 1 is 1. Alpha 3 by 1 minus 4 is minus 3. Now let us consider this ratio as k. We say this is k. Okay, so from this equating each fraction with this k, we can get the values of alpha 1, alpha 2, alpha 3 with respect to k. So alpha 1 value, you cross multiply this 1 with this k. Okay, so 1 into k, that is k. Alpha 2 means 1 into k, cross multiply. So that is also k. Alpha 3 means minus 3 into k, that is minus 3k. Now, if we know the k value, then only we can give the particular values of alpha 1, alpha 2, alpha 3. To find the k value, I consider the third equation, because for making RCM, I did with the first two equations. So the unused equation is third equation here. So the unused equation we have to substitute. After getting this ratio, the values in with respect to k, we need to use those values to get the value of k in the unused equation. Okay. So here the unused equation is third equation. Third equation is alpha 1 plus 2 alpha 3. Now substitute the values. Alpha 1 is k and alpha 3 is minus 3k. So plus 2 into alpha 3 is minus 3k equal to 0. That is k plus minus 6k equal to 0. We are getting minus 5k equal to 0. Now understand, the product of minus 5 into k is 0. So when a product goes 0, if any of the values goes 0. No, so here minus 5 cannot be 0 since it is a constant. Minus 5 is always minus 5. So only possibility is k should be 0. Okay. So our k goes 0. Now substitute this k values in alpha 1, alpha 2, alpha 3 to get the particular values. So all the alpha is 3 values are with respect to k. So our alpha 1 is equal to k. K is 0 means alpha 1 is 0. Alpha 2 equal to k. K is 0. So alpha 2 is also 0. Alpha 3 is minus 3 into 0. That is also 0. Now we get all these alpha 3 alpha values as 0. So we can say V1, V2, V3 are linearly independent. Similarly, another problem, show that in V3 of R, the vectors 1, 4, minus 2, minus 2, 1, 3 and minus 4, 11, 5 are linearly dependent. Here we need to prove linearly dependent. So recall the definition. We consider the linear combination to be 0, and if we find at least one alpha I not equal to 0, then we say the vectors are linearly dependent. Now see, we consider the given vectors as v1, v2, v3. So v1 is 1, 4, minus 2. v2 is minus 2, 1, 3. And v3 is minus 4, 11, 5. Now we need to prove v1, v2, v3 are linearly dependent. So we assume the linear combination of v1, v2, v3 as 0. That is alpha 1, v1 plus alpha 2, v2 plus alpha 3, v3 as 0. Substitute the values of v1, v2, v3. So instead of v1, substitute 1, 4, minus 2. v2, minus 2, 1, 3. And v3 as minus 4, 11, 5. Okay. So we get the equations by simplifying the first elements, second elements and third elements, and we get the three equations. So consider the first elements, alpha 1 minus 2 alpha 2 minus 4 alpha 3 equal to 0. First equation. Second equation with respect to the second elements, 4 alpha 1 plus 1 into alpha 2, that is plus alpha 2 plus 11 alpha 3 equal to 0. Now with respect to third values, minus 2 alpha 1 plus 3 alpha 2 plus 5 alpha 3 equal to 0. Again, we need to solve for the three equations. Equation 1, 2, and 3. Solve these three equations. We get the alpha values. Again, consider the three equations. Here also I find these two equations different. So I consider RCM with respect to equation 1 and 2. Now do. So we can, the values are minus 2, 1. Here minus 4, 11. 1, 4. Again minus 2, 1. Minus 2, 1. Minus 4, 11. 1, 4. And again minus 2, 1. Now our alpha 1 by this determinant. Okay. So minus 2 into 11 minus 22 minus of minus. So plus 4. Minus 22 plus 4 equal to alpha 2 by this determinant. Minus 4 into 4, that is minus 16. Minus 1 into 11 is 11 equal to alpha 3 by here 1 into 1, that is 1. Minus of minus goes plus. 2 into 4 is 8. So our alpha 1 by minus 22 plus 4, that is minus 18 equal to alpha 2 by minus 16 minus 11 is minus 27 equal to alpha 3 by 1 plus 8 is 9. So we can divide by 9 or minus 9. I divide by minus 9. Okay. So what I get, if I divide the denominators by minus 9, this is alpha 1 by 2. Here alpha 2 by 3. And here alpha 3 by minus 9. I divide by minus 9. So I get minus 1. Now consider this as equal to k. We say. Now equating each fraction with this k, we can get the alpha values. Alpha 1 with respect to k, we can get 2 into k. So our alpha 1 is 2k. Alpha 2 is the denominator 3 into k, that is 3k. Alpha 3 is minus 1 into k, which is minus k. Okay. Now this is our alpha values. All are in terms of k. So to find k, what we will do? We'll substitute this in the unused equation. Here I didn't use, here I used only first and second equation. So these two equations are already used. The unused equation is equation 3. So I substitute these values in equation 3. So what I get when I substitute? So minus 2 into alpha 1, that is 2k, plus 3 alpha 2, plus 3 into alpha 2 is 3k, plus 5 into alpha 3. 5 into alpha 3 is minus k equal to 0. Substitute in the third equation. So I get minus 4k plus 9k minus 5k equal to 0. Now what happens? The left hand side minus 4k minus 5k is minus 9k. So I get 9k minus 9k equal to 0. So here the left hand side also is going 0. Okay. So irrespective of this k value, it is going 0. So we can say this equation is satisfied for any value of a k. any value of k, this is satisfied. If the left hand side, in the previous problem, if you see, we got minus 5k equal to 0, then we understood that since minus 5 is not equal to 0, k goes 0. Here it is not like that, okay? The left hand side is completely going 0. So irrespective of the k value, the equation is satisfied. Therefore, for any value of k, this is true. So let's suppose we substitute k equal to 1. We put k equal to 1. For example, you can substitute any value, okay? K equal to 1, a non-zero value we choose. Then what we get in this alpha values, alpha 1 is 2 into 1, that is 2. Alpha 2 will be 3 into 1, that is 3. And alpha 3 is minus 1. So we can substitute for any value of k not equal to 0. Any non-zero values of k, this is true. Now we are getting the alpha i's not equal to 0, no? So alpha i's are non-zero values, non-zero alpha values. We are getting non-zero alpha values, even the linear combination goes 0. Non-zero alpha i's we are getting. Therefore, we can say our V1, V2, V3 are linearly dependent. Linearly dependent. Okay. So if all the linear combination goes 0, when all the alpha is also 0 means linearly independent. All the alpha is not 0 means linearly dependent. Okay. Practice well.